Hello, my people. How are we doing today? Let's go ahead and get started on some basic rules of differentiation. This is 3.1. I think your book calls it derivatives of polynomial and exponential functions, which is, probably a pretty good title too. Just a little bit too long to fit across the top here. And what we're going to be doing is, this is basically just the basic ones, okay? And so this basically starts us off from where we left off in terms of doing the derivatives in terms of limit definition, and starts to sort of teach you the shortcuts that you arrive at after you do it by limit definition a bunch of times. You do it by limit definition enough times, and you start to recognize certain patterns, and certain things are just sort of intuitively known. So let's go ahead and just sort of jump right into the first couple. Now, K in this particular instance refers to a constant, okay? And so if we're going to take the derivative of a constant, it should be pretty plain the fact that it's 0. Because if I have y is equal to k as a function, that's like y is equal to 2, y is equal to 17, y is equal to 1,380. It doesn't matter. If it's y is equal to a constant, that's telling you that the y value is always the same, and it's a horizontal line. Well, what is the slope of a horizontal line? Well, the slope is 0. Okay. Now this looks all complicated in terms of the notation, but really all this means right here is that given any derivative that you are asked to take, you can do it term by term. And of course we went over this a little bit in terms of being able to do limits term by term. And of course you can do derivatives term by term because they are special limits. They are a specific kind of limit, based upon the idea that we define derivatives by the limit definition. And so if you're given a polynomial, we can just go ahead and just do it term by term. And we'll get back to this one. It's very, very, very straightforward. Now this one has to do with examples like y is equal to 3x squared. Okay? If I'm going to take the derivative of 3x squared, what happens to the 3? Well, all this says is that if you have a constant sitting out in front of a function that you want to differentiate, that you want to take the derivative of, then basically, just like when a limit you can take a constant and sort of pull it out in front, right? That's exactly what we've done here, and therefore the derivative of f is simply f prime. So the coefficient just sort of comes along for the ride. Now these two are really the meat of 3.1. These are the ones that are actually, the ones that, might take you a few seconds to sort of get your mind around. This one has a special name. It's called the power rule. Okay? And the power rule, and I explained it to y'all last year. I don't know, I was discussing with one of y'all on the Skype session on Saturday. Here's the thing. I understand that a lot of what is taught in April and May doesn't stick because by that time during the year you guys are fried, okay? But I'm just hoping that some of this is familiar. And when I explained the power rule, I showed you why it wasn't really a proof, it was more of a demonstration as to why it made sense. And I did that demonstration with respect to Pascal's triangle, and I'm going to show you that again right now. But let's say I have y is equal to x to the 7th. It's the derivative of x to the 7th is 7x to the 6th. If I have, y is equal to x to the 27th, it would be 27 times x to the 26th. So you just pull that, you sort of pull that exponent down and then subtract 1 from the exponent, okay? And this one, basically, as far as I know, with the exception of y is equal to 0, which was kind of an unimpressive and underwhelming case to actually talk about, this is the only function whose derivative is itself, okay? Now, I can't really tell you why this is until we get to about section 3.5 or 3.6. I forget which one. But rest assured, when we get there, I will explain why this is. But for right now, the derivative of e to the x is equal to e to the x simply because I told you that it was, okay? But I promise I'll explain this in due time. So we're going to go ahead and take these, and we're actually going to do some examples. That is after I explain the power rule, okay? Now, remember that when we're dealing with taking derivatives of powers, I know that the derivative of x to the n, if I want to put it in terms of the limit definition, sort of in general, is going to be the limit as h goes to 0 of x plus h to the n minus x to the n, all of that over h, right? So if this is x to the third, this becomes x plus h to the third. If we have x to the fourth, this is x plus h to the fourth. If we have x to the fifth, this is x plus h to the fifth, and so on and so on and so on. So it might be a good idea to go ahead and take a look at binomial expansion, okay, in terms of Pascal's triangle. Now, Pascal's triangle, if you do not remember, is this little guy right here. And you get the numbers in Pascal's triangle starting with 1 on the outer rims. And every time you go down one level, you add the two numbers that are above it. So 1 plus 1 is 2. 2 plus 1 is 3. 3 plus 3 is 6. 3 plus 1 is 4. 6 plus 4 is 10. 4 plus 1 is 5. And that's how you construct it. So I could keep going, and I could go 1, 6, because that's 1 plus 5. 15, and that's 5 plus 10. And 20, and that's 10 plus 10. And then, of course, 15, 6, and 1. Now, what makes this really, really special is the fact that these are the coefficients of a plus b to whatever, okay? So this right here is a plus b to the 0, okay? This right here are the coefficients of a plus b to the first. Well, you ought to recognize just from all the times that you have seen a binomial squared. A binomial squared, when the coefficients are 1 and 1, is 1, 2, 1. And these are the coefficients of a plus b cubed, a plus b to the fourth, a plus b to the fifth, a plus b to the sixth. Now, all of that you should remember, okay? But what I want to do is I want to talk about it not in terms of a plus b, but x plus h, okay? Now, remember, these represent sort of the first several possibilities of what that binomial expansion could be in the numerator, right? So let me go ahead and fold this so we can actually put it right underneath here and actually show it all at once. So basically, you know, this is basically the expansion if this is x plus h squared. This is the expansion if this is x plus h cubed, right? Well, notice that, let me sort of flatten out that crease right there. Notice, let's go ahead and sort of draw lines through here so it actually winds up just being a little bit neater. Probably should have done this when I constructed it, but you know, whatever. It doesn't take that long to do it. Okay, so we know that those are possibilities of what can occur in the numerator. Okay, now we recognize that if this is x plus h to the first, then this is x to the first, so we have minus x right here, right? And of course, that means that this and this are going to cancel, and all that's left is h. I know that on this row, that numerator is going to also have a minus x squared, which means that after you do the binomial expansion, you're left with this, and you're left with 2xh plus h squared. In here, you're going to have minus x cubed. On the fourth line, you're going to have minus x to the fourth, and on the fifth line, you're going to have minus x to the fifth, and so on and so on. And of course, that always cancels with that first term of the binomial expansion, leaving what's left in here. Now, if you remember that, if you recognize the fact that all of these terms that are left have an h in it, well, that's pretty significant because you have an h right here in this denominator that needs to be canceled out, okay? So what happens here is this h goes bye-bye and becomes a 1. This h goes bye-bye, and one of those h's goes bye-bye. So that h goes completely gone. That one is reduced from the power of 2 to the power of 1. This one goes bye-bye. That becomes 2, or that becomes 1. And that exponent right there goes from 3 to 2, right? If you go ahead and like factor out the h. Okay? And the same thing occurs all the way down, right? And this becomes squared, and that becomes third, and that becomes squared, and that becomes third, and that becomes to the fourth, right? Well, notice something. Notice that after you've done all this simplification, these expressions, you're taking the limit as h approaches 0. So what happens is all of these terms right here still have an h in them. So all of those terms are going to basically go bye-bye when you actually evaluate the limit after you've done the binomial expansion and all the simplification you can do. And look at what's left. 2x, 3x squared, 4x cubed, 5x to the fourth. Okay? That's why the derivative of x squared is 2x. The derivative of x cubed is 3x squared. The derivative of x to the fourth is 4x cubed. The derivative of x to the fifth is 5x to the fourth. And of course you can count on this pattern continuing all the way down, which is why when you actually take the derivative of x to the n, it winds up being nx to the n minus 1. Okay? Now, is your teacher going to ask you to actually execute that demonstration? Because it's close to a proof, but we didn't do it as abstractly enough in order to actually make it a proof. Your teacher is not going to ask you to do that demonstration. You're not going to be asked to do anything like that on the AP exam, but you know me, I want you to understand why something is the case, because if you understand why it's the case, you're more likely to remember it. So there you go. So the only thing left for us to do now is to actually take the rules that we've actually seen and the one that, of course, that we've demonstrated and just do some examples. Okay? So let's go ahead and let's say we have f of x is equal to, 2x cubed minus x plus 3. Okay? And I'm asked to take the derivative of that. And so f prime is equal to what? Well, remember that we have several different principles, several different rules of differentiation that we're going to be using here. Now, obviously, this is several terms, okay? Several terms means that we're going to be using the one that tells me that if I take the derivative of f plus g, I wind up being able to do it term by term, okay? That means that I don't have to take the derivative of the whole thing all at once. Who would want to do that? Who could do that? Okay? You can actually do it term by term. But notice also that this one has a leading coefficient, right? There's a coefficient out here that's not 1. So we also are using this rule of differentiation where basically that constant will come along for the ride, okay? But we're also, in that last term, taking the derivative of a constant, and we need to know that that is indeed 0. So all we really have to do is we have to say, well, what's the derivative of 2x cubed? Well, I know that the 2 comes along for the ride, and the derivative of x cubed is 3x squared, because you bring down the 3 and turn the cubed into a square. So that winds up being 6x squared. Now that middle term right there is linear, okay? Now the derivative of anything linear is very, very easy. It's the coefficient, right? Or, you could employ the power rule, bring down the exponent, and then subtract 1 from the 1 exponent, and you get 1x to the 0. So it actually does officially abide by that rule, but you don't really have to use it. It's linear, so basically its coefficient is its derivative. And then, of course, and you don't have to write this, but basically that is there just for emphasis, but we don't write it. So the 2x cubed becomes 6x squared when you take the derivative. Negative x becomes negative 1, and positive 3 has a derivative of 0. And therefore we have the derivative of that polynomial. Now, that's of course a relatively easy one, and they don't really get all that complicated in this particular section, but let's go ahead and look at a few more examples. Let's go ahead and look at, what shall we do? How about g of x is equal to x minus 4 and 3x plus 1? And you're thinking to yourself, well, I know we're coming down the pike towards the product rule, but we don't know the product rule yet. You're right. You don't know the product rule yet. Or you don't, quote, know the product rule. Okay? But this is just two binomials that can be easily FOILed in order to get us to 3x squared. Now the outer is going to be x, the inner is going to be negative 12, so that's negative 11x minus 4, okay? So you need to remember that sometimes it's good to go ahead and change the form, and we'll go ahead when we start doing the product rule, we'll come back and I'll show you the fact that getting the derivative this way and getting it by the product rule are actually the same thing. So basically we've simplified it, going from factored form into polynomial form, and now we need to do it term by term. So 3x squared becomes 6x minus 11 plus 0, and here we have the derivative of g of x. Now, you need to remember what the derivative says about the original function, okay? That derivative tells us that for any x here, okay, this will describe the slope of this original function. So if you want to know the slope where this has its y-intercept, which is, 0, negative 4, you plug in 0 right here, and we can see the fact that this, if I were to evaluate the derivative function at 0, I would get negative 11. So, you got to remember that the reason why the derivative is a function is because this does not have a constant slope. This has a variable slope, and as such, the representation of its slope needs to be variable. It needs to be a function, right? So the slope is not going to be everywhere the same on this, and therefore we need a function to tell us what the slope is on the original function at any particular x. And here I've actually done it for x is equal to 0. Okay, well I know the slope at 0, and I know that 0, negative 4 is its y-intercept. So let's say that I was asked for the equation of a tangent line at that y-intercept. Well, what do I need in order to have the equation of a line? In order to find the equation of a line, I need two pieces of information. I need point slope. That's all I need. Okay? So I need y minus y1 is equal to m times x minus x1. And on the AP exam, if you're just asked for an equation of a tangent line, that's all you need to give them. You don't need to put it into slope-intercept form unless on the multiple choice section of the exam, of course, the answer choices are all in slope-intercept form. Then, of course, I would go ahead and recommend switching it. But switching it up is really not that big of a deal. This is y plus 4 is equal to a negative 11x, or y is equal to negative 11x minus 4, right? So there's your slope-intercept if you're asked for it. Okay. We're coming up on about 18 plus minutes here, so I'm going to go ahead and call it quits on this particular video. Those are a couple of examples on top of a demonstration of why the product rule is what it is. In the next one, we're going to do a little bit more robust examples and a few more examples of the equation of the tangent line. May get it all done in the next video. It may go on into 3 videos, but guys, I hope that's helpful. Leave a comment or shoot me an email if it is not.